Hello YouTube! As you may be aware, NASA's New Horizons probe has just made its closest pass of Pluto and has given us detailed images of it for the very first time. So I thought this was a good time to deal with the question, is Pluto a planet? Pluto was once classed as a planet. When I was a little kid, interested in space, I would read about the 9 planets of the solar system. But in 2006, Pluto was demoted. The International Astronomical Union, or IAU, came up with a precise definition of planet, and Pluto didn't count. Instead, it's a dwarf planet. Dwarf planet is an unfortunate name, because you'd think, oh, dwarf planet, that must be a kind of planet. No, dwarf planets aren't planets. It's a completely separate category. So that might be a little bit confusing at first, but they're not planets. This generated some controversy, and to this day some people argue that the IAU's definition of planet is flawed. So that's what we'll talk about in this video. What is a planet? I should note that I come to this from the point of view of philosophy. Philosophers never really had anything to say about this debate, which I think is interesting because it seems to me that this is exactly the kind of thing philosophers would enjoy. How should we define the term planet? That's a classic example of conceptual analysis. Anyway, why was Pluto demoted? Well, Pluto had always been something of a renegade in our solar system. It wasn't like the other 8 planets. Pluto is much smaller in both size and mass. Here are the sizes and masses of the planets. The ME here just means Earth masses. So Neptune is about 17 times the mass of the Earth. Pluto, as you can see, is very small. In fact, it's even smaller than the Moon, although I don't have that here. Its orbit is much more eccentric than the other planets, which means that its perihelion, the point at which it's closest to the Sun, is much smaller than its aphelion, the point at which it's furthest from the Sun. I found this image online, and you can't really see it here, but it actually comes in closer to the Sun than Neptune at times. It also has a highly inclined orbit. The angle of its orbit relative to the ecliptic plane of the solar system is greater than the other planets. So here's a chart showing the orbital eccentricities and the orbital inclinations of all the planets. As you can see, again, Pluto stands out. Pluto is a bit of a rogue. But okay, you know, it's a small planet with a funny orbit. Big deal. Problems started to emerge when a number of similar objects in the same sort of orbit were discovered. These objects comprise the Kuiper belt, which is basically an asteroid belt out beyond Neptune. This is a picture from somewhere online. You can see Neptune here with the green orbit, and outside it there's the Kuiper belt. It contains hundreds of thousands of small asteroids, but also a number of larger, nearly planet-sized bodies. Makemake, Salacia, Haumea, Orcus, Varuna, Vada, Ixion. There are probably hundreds of these things. So we're finding loads of objects that are very much like Pluto. Are all of these objects planets? Or should these objects, including Pluto, be considered part of a separate class? Pluto was the misfit of the solar system, but it fits in well with these large Kuiper belt objects. This concern about Pluto's status was pretty much ignored until 2005, when the Kuiper belt object Eris was discovered. Eris was, at the time, thought to be bigger than Pluto. So we can't really ignore these classification problems anymore. If Pluto is a planet, surely Eris is a planet too. And for a short while, it was actually considered to be the 10th planet. Now, actually, I should add, I think new data has shown that Eris is actually slightly smaller than Pluto, although it does still have a greater mass. But obviously, even if it is smaller, the problem still remains. It seems totally arbitrary to say Pluto is a planet, but these other things aren't. So you can see, you know, the problems mounting for Pluto. It's interesting to contrast the story of Pluto with that of Ceres. Back in 1781, only 6 planets were known: Mercury, Venus, Earth, Mars, Jupiter and Saturn. The approximate distances of the planets from the Sun were also known, and it was noticed that the distance of each planet follows an interesting sequence. So consider this sequence. Okay, you can see it's 0, 3, 6, 12, doubling each time. We'll now add 4 to each number in this sequence, giving you 4, 7, 10, 16, and so on. The distance of each planet from the Sun follows this pattern almost exactly. So here's a chart. Now, on the left here is the prediction according to this sequence, and on the right is the real distance in AU. AU is astronomical unit. AU means the distance from the Earth to the Sun. So Mercury is about 0.4 AU from the Sun. It's about 0.4 the distance from the Sun that the Earth is. Venus is about 0.7 and so on. And you can see that planets fit this pattern really very well. Now, the idea that each planet is placed at a distance according to this pattern was known as Bode's law. And Bode's law received an enormous boost in 1781 when William Herschel discovered Uranus. It fits the pattern almost exactly. But there's an obvious problem here. There's a gap between Mars and Jupiter. So this led to the prediction, well, there must be a planet about 2.8 AU from the Sun. So people started looking, and in 1801 Giuseppe Piazza found an object orbiting at just the right place, which was dubbed Ceres. It was about 2.77 AU, and it was considered a planet. Still, there were some problems for Ceres. It was known that Ceres was relatively small, much, much smaller than the other planets, at any rate. And then shortly after the discovery of Ceres, astronomers discovered a number of other objects in the same area: Pallas, Juno, and Vesta. Now this led Herschel to suggest that these aren't quite like the other planets in the sky. Maybe they're not proper planets. And he suggested the term asteroid. That didn't catch on for some time, for one thing because the discoveries of other similar objects dried up for several decades. But in the mid-1800s, a whole host of other objects in similar orbits were discovered, and it became sort of obvious that there would be hundreds, thousands of these things. So clearly these objects are a class of their own. They're unlike the other 7 planets that were known at the time. So Herschel's term asteroid was adopted, and we now call these objects the asteroid belt. Incidentally, regarding Bode's law, it turned out that Neptune didn't fit. I'm not sure there's any agreement on exactly why the other planets follow that pattern. I think some astronomers just say it's just a coincidence. But anyway, that was a short history of Ceres. It was originally regarded as a planet, but it became clear that it had much more in common with these other objects than with the planets, so it was reclassified. And this mirrors what happened with Pluto. If we want to class Pluto as a planet, we'd have to include possibly hundreds of other objects in the Kuiper belt as well. But these objects, while they have a lot in common with each other, don't really have much in common with the other planets. So it seems like a separate classification is reasonable. But, of course, it's not so simple. The other way to look at it is that even ignoring Pluto, there's already a great deal of variety in the planets. There are 4 terrestrial planets, 2 gas giants, and 2 ice giants. Which are more similar, Mercury and Jupiter, or Mercury and Pluto? Well, my immediate feeling is that all things considered, Mercury and Pluto are more similar. I'm not really sure how I would defend that claim, but that's just how I feel about it. So, we shouldn't overstate the similarities between the 8 planets that we know of. And similarly, we shouldn't overstate the similarities between Pluto and other Kuiper belt objects. Pluto has an atmosphere, it exhibits geological differentiation, which means its interior structure is separated into layers of core and mantle and crust. It has moons, it's about 70% rock, whereas I believe that most other Kuiper belt objects are mostly ice. So there's a bit of a stalemate here. There are good reasons to reclassify, but good reasons to keep Pluto as a planet. Obviously, if we do say that Pluto is a planet, we'll have to say that Eris and Ceres and Orcus and Makemake and so on are planets too, but is that really such a big deal? Why shouldn't they be planets? Well, at this point, it's clear that we need a more precise definition. What exactly is a planet? What is it exactly? Well, as I mentioned, this was answered in 2006 by the IAU. Here's the definition that they adopted. A planet is a celestial body that meets the following criteria. It is in orbit around the Sun. It has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium nearly round shape. And it has cleared the neighbourhood around its orbit. Okay, so this second condition, number 2, basically just says that the planet has to be spherical. Its shape has to be determined by gravity rather than by the chemical properties of its materials. If you look at many asteroids, you'll see that they've got weird shapes. They jut out in all sorts of random directions. Planets have to be rounded. No problem for Pluto there. Clearing the neighbourhood, third criterion, this basically means that a planet has become the dominant gravitational force in its orbital zone. So there are no other large objects in its orbital zone that orbit independently of it. When planets form, they accrete objects, or they can kick objects out of their orbit, ejecting them into space, or they can capture objects and have them as satellites. So if you look at the 8 major planets, aside from their satellites, they're pretty much isolated. But as we saw, Ceres is part of the asteroid belt. Pluto is part of the Kuiper belt. There are a whole host of other objects in Pluto's orbital zone, so Pluto hasn't cleared its neighbourhood. According to this definition, then, it isn't a planet. Instead, it's a dwarf planet, which, as I mentioned, is a separate classification. Dwarf planets are not planets. The IAU defined a dwarf planet as a celestial body that is in orbit around the Sun, has sufficient mass for hydrostatic equilibrium, is rounded by gravity, has not cleared its neighbourhood, and is not a satellite. So, this definition of planet clearly has benefits. When you look at the solar system as a whole, a reasonably clear picture does start to emerge. Just looking at it pre-theoretically, we would probably divide it into 8 planets, their satellites, the asteroid belt, the Kuiper belt, the Oort cloud, the comets, and so on. Now the IAU definition fits very well with this picture. Pluto becomes a dwarf planet, sitting with various other dwarf planets and asteroids in the Kuiper belt. However, I believe that when the IAU voted on this definition, most IAU members weren't present, and the vote was very close. There were only a few votes in it. So unsurprisingly, there are quite a lot of objections to this definition of planet. Now, before we consider these, it's worth asking, what are we actually looking for in a definition of planet? What would count as a good definition? So it's worth making our criteria explicit, and I think there are basically 5 criteria that we could all accept. First of all, it must respect paradigm cases. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune must all count as planets. These are the paradigm planets. So if our definition rules out any of these, something's gone wrong. Second, we want planet to name a natural category. One way of defining it would be to say, a planet is a member of this set: Mercury, Venus, Earth, Mars, Jupiter, and so on. That's obviously unacceptable, because it's just, that's not really a proper definition, is it? Another might be, a planet is any object orbiting a star with a radius larger than 1,500 kilometres. Okay, that's not so bad, but there's still the question, what's so special about 1,500 kilometres? We're just drawing an arbitrary line there, and we don't want our definition of planet to be arbitrary. We want the definition to carve nature at its joints, to use Plato's famous phrase. Third, the definition should have some respect for standard usage. Suppose we define planet as anything that orbits a star. Okay, that's clearly not acceptable. That would end up classifying even the tiniest chunks of rock in the asteroid belt as planets. Fourth, classification rules should be clear, simple, and applicable in scientific research. It shouldn't take a great deal of research to figure out whether or not something is a planet. So if we have to drill into the object's core to figure it out, then that's not a good definition. And this point also, this also includes the point that it shouldn't be open to individual opinion whether or not something counts as a planet. For instance, an object is a planet if it orbits a star and has beautiful geological features. Well, what counts as beautiful geological features. Obviously, that's not something open to empirical testing, so that has no real place in science. Finally, fifth, it shouldn't be limited to our solar system. We should be able to look at other things beyond our solar system and say, these are planets and these aren't planets. Have I included all of the appropriate criteria there? Well, it seems to me that many people who defend the IAU definition tend to appeal to criteria other than these. One standard argument in favour of the IAU definition is that it keeps the number of planets low. It means we only have 8 planets. As we saw, there are many other objects like Pluto, which means that any non-arbitrary definition of planet that classes Pluto as a planet will class possibly hundreds of other objects as planets. A number of astronomers have suggested that this would be a problem, and that the number of planets should be kept low. So that suggests a 6th criterion: there should not be much more than 8 planets. Definition should keep the number of planets low. I think that this criterion is ridiculous. What's wrong with hundreds of planets? Why shouldn't the solar system be totally crowded? I mean, there are hundreds of thousands of asteroids, that's not a problem. Why would hundreds of planets be a problem? The main point that I've seen raised here is educational. When kids are in school, they're taught about the planets, and 8 planets is perfectly manageable, but hundreds is not something you can try to make kids learn. Okay, 4 terrestrial planets, 2 ice giants, 2 gas giants, that makes for a nice, simple educational program. This is a silly argument. Think about the number of countries in the world, the number of kings and queens in the past, the number of living species in biology. There are hundreds, thousands. How do we teach kids about them? Well, you focus on the ones that are most important for your general educational purposes. If there turn out to be hundreds of planets in the solar system, that doesn't mean you'd have to teach kids about every single one of them. You focus on the biggest ones, or the ones that are closest to us, or the ones that have interesting features, or whatever. In any case, I would suggest that, if anything, massively expanding the number of planets would actually encourage learning. Because 8 planets is easy. Get students to memorise the names in the order and a few important facts, like Jupiter is the biggest and Saturn has the biggest rings, and that's that. But if there are hundreds of planets, you can't go through them all. You have to leave possibilities open. And that means there are whole vistas out there that people have to discover on their own. Hundreds of worlds out there, in the Kuiper belt, in the Oort cloud maybe. It's invigorating. It encourages people to do their own reading. So I think that this criterion is nonsense. There's no reason necessarily why we have to keep the number of planets low. Another criterion I've sometimes seen suggested is that the classification system has to give a picture that's in some sense elegant or beautiful. Mike Brown seems to suggest something like this in a blog post entitled "So Is Pluto a Planet After All?" And he says that there is beauty in 8 planets, there is order in 8 planets. So maybe this suggests the definition should give us a sort of elegant or beautiful classification of the solar system. Of course, this criterion is totally subjective. Personally, I think a classification system that allows hundreds of planets is just as beautiful. I tend to be attracted to that kind of chaos. So I'm not persuaded by either of these criteria. I think the 5 that we've seen are quite sufficient. So let's turn to some problems for the IAU definition. Here it is again. Now, first of all, it's obviously too restrictive since it's limited to our solar system. This is the first condition that a planet is an object orbiting the Sun. I find it kind of incredible that none of the astronomers writing this definition picked up on this problem. That's just, how did they miss that? But it's easy to generalise it, so instead we say, okay, a planet is an object in orbit around a star, right? That's easily sorted. A second problem is that the definition is too inclusive, since it would class a star orbiting another star as a planet. I think we know, in fact, that there are brown dwarfs that orbit other stars, but brown dwarfs are not planets. So we'd want to add that the object is not a star. The defining feature of stars is nuclear fusion, so we'd probably want to add a condition that the object not have a mass large enough that it can sustain nuclear fusion. I like to call this the IAU plus definition, so A planet is an object in orbit around a star, surrounded by its own gravity, has cleared its neighbourhood, and does not have sufficient mass to at any point sustain nuclear fusion. I think that this preserves the spirit of the IAU definition while fixing those obvious problems. So this is kind of, a plausible definition here. Now, the main objections to this definition concern the third condition, that a planet must have cleared its neighbourhood. This is the idea that any other material in the orbital zone has either been ejected or accreted into the planet, or captured as a satellite. And an immediate objection to this was that many other planets in the solar system haven't cleared their neighbourhoods either. There are thousands of asteroids called Trojans that orbit in Jupiter's orbital zone, and there are possibly loads of other Trojans that orbit in Neptune's. Neptune also has what are called Plutinos. So you might remember that Pluto's orbit crosses Neptune. This led Alan Stern to say that if Neptune had cleared its neighbourhood, Pluto wouldn't be there. So it's not just Pluto. There are a whole bunch of other objects that cross Neptune's orbit in this way, called Plutinos. So this is a problem, because obviously Jupiter and Neptune are planets, but Jupiter has these Trojan asteroids, Neptune has a bunch of Trojans as well, and it has these Plutinos. Now I think that this objection rests on a misunderstanding. So let's consider Neptune and Pluto. The point here is that Neptune is gravitationally dominant. Pluto's orbit is fixed by Neptune's. When the solar system formed, Neptune moved out and it ejected some material into space, but it also forced some orbits, including Pluto, into a sort of particular special kind of orbit. Pluto orbits in what's known as a 2 to 3 mean motion resonance with Neptune, which just means that every 3 times Neptune orbits the Sun, Pluto orbits it twice. So Pluto and the other Plutinos are under the control of Neptune's gravity. And the same is true for the Jupiter Trojans. These orbit at what are known as Lagrangian points. So here's a little diagram. Now, there's Jupiter and there's its Trojans, and they orbit here in a stable orbit that's determined by Jupiter's gravity. They don't ever hit Jupiter because they orbit with the same orbital period. It takes Jupiter 12 years to go around the Sun. It takes the Trojans 12 years to go around the Sun. So they're always in the same place with respect to Jupiter, basically. And the reason why they're stable here is that at this point, the Sun is pulling them at a particular force, but that's kind of balanced by the lesser force that Jupiter is exerting. So this particular spot here is stable. So we can say that Jupiter has cleared its neighbourhood because it's gravitationally dominant over these Trojans. The other point here is, just look at the masses of the various planets. Jupiter is millions of times more massive than all of its Trojans combined. Pluto doesn't greatly exceed the mass of other Kuiper belt objects, even taking them one by one. Here's a chart by Stephen Soter showing the masses of various bodies divided by the masses of all the other bodies in their orbital zones. Now notice that these here are orders of magnitude. So for the values for the planets are all over 5,000. For Pluto, Ceres and Eris, it's less than 1. Now that is pretty striking. I think that provides a pretty clear line with which to distinguish planets from non-planets. So I think that clearing the neighbourhood is, it doesn't apply to the 8 planets, or rather, it does apply to the 8 planets, but not to Pluto. There are a few other objections to clearing the neighbourhood. We saw that an important criterion for a planet is that a planet should be a natural category, so our definition should carve nature at its joints. Now the trouble is that a lot of people feel that there's some arbitrariness in the requirement to clear the neighbourhood. Whether or not a planet can clear its neighbourhood depends on how far away it is from its star. And this is kind of obvious when you think about it. The further away a planet is, the larger its orbit will be, and the larger its orbit, the more space it has to clear. Now if Pluto were as close to the Sun as Mercury, it would probably have cleared its neighbourhood, so it would be a planet. On the other hand, if Mercury or Mars were as far away as Pluto, they would not have cleared their neighbourhoods, so would only be dwarf planets. In fact, if the Sun was bigger, an exact copy of Earth in the habitable zone from the Sun would not have enough mass to clear its neighbourhood. So there seems to be something unnatural about this. An object's status as a planet doesn't depend on its intrinsic properties, but on how far away it is from the Sun. So instead of looking at what the object is in itself, its status as a planet depends on what's going on around it. Now this problem is exacerbated when we realise that it's possible for objects to change their orbits. Suppose a planet which has cleared its neighbourhood drifts into a new orbit, or is wrenched into a new orbit due to some cosmic cataclysm. This kind of thing can happen. Well, it might fail to clear its new neighbourhood. So then a planet has become not a planet. As Alan Stern puts it, identical objects don't classify identically at different locations. So the suggestion is our definition of planet should reflect its intrinsic properties, its geophysical properties. An object's classification as a planet shouldn't be able to change just because it's changed location. So Stern is appealing to another criterion for a good definition. For Stern, a definition must also meet the definition must not allow an object to be classified as a planet in one place if it would not classify it as a planet in another place. Or more generally, whether or not an object is a planet must depend on its intrinsic properties rather than its dynamic or relational properties. Stern has suggested a definition that meets this criterion, which he calls the geophysical planet definition. This says that a planet is any oh, sorry. God, I got a bit of a cough. Had a tickle in my throat. Anyway, geophysical planet definition. A planet is any object in space that is massive enough to be rounded by its own gravity, but not so massive that its core can at some point ignite in sustained nuclear fusion. The qualification at some point allows for there to be proto-stars in which fusion has not yet started, plus dead stars and brown dwarfs that once sustained nuclear fusion but don't anymore. This definition focuses on the geophysical properties of planets. It doesn't matter where a planet is or what its history is or whether there's anything else like it in its orbital zone. On this definition, Pluto and many other objects are planets. Now, in my view, this definition is not very well motivated. I don't see why we should accept this criterion that a good definition has to ignore dynamic and relational properties. Certainly, whether or not a planet has cleared its neighbourhood is a dynamical property, but I don't agree that the definition is flawed just because it appeals to dynamical properties. Our classification schemes often appeal to purely dynamical properties. For instance, pretty much everybody agrees that a satellite is not a planet. Jupiter's moon, Ganymede, is the largest moon in the solar system. It's bigger than Mercury. It's physically differentiated into a core and a mantle, has an internal ocean, a magnetic field, and even a thin atmosphere. Nobody calls Ganymede a planet. Ganymede is a moon. But if you swapped Mercury and Ganymede, Ganymede would clearly be a planet, and Mercury would clearly be a moon. Furthermore, a planet could become a satellite. If a large gas giant moves out over time, it might trap a planet in its orbit. Surely we'd say that this is now a moon. Now, to be fair, some supporters of a geophysical definition have just bitten the bullet on this point. Phil Metzger, I believe, has suggested that, yep, we should class moons as planets. To say that something isn't a planet just because it orbits another planet is too arbitrary, according to Metzger. Why shouldn't a planet orbit a planet? After all, we're happy to say that stars can orbit stars. Furthermore, we know that there are binary planets. So what's the big distinction between a binary planet and a planet-moon system? Well, it's often based on where the barycenter, the centre of mass of the system, is located. Objects in a system will orbit the barycenter of that system. So when we say that the moon orbits the Earth, that's technically false. the Moon orbits the barycenter of the Earth and the Moon. And this allows us to distinguish planets with moons from binary planets. Two objects are a planet and a moon if the barycenter is located within the larger object. At the moment, the barycenter of the Earth and Moon is about 1,500 kilometers within the Earth, so the Moon is a moon. Two objects are binary planets if the barycenter is located outside both objects. But now again, doesn't this just seem a bit arbitrary? And it gets worse because the Moon is drifting away from the Earth, and eventually the barycenter will drift beyond the Earth. So at that moment, does the Moon become a planet? Metzger would suggest that this is just silly. Just call the Moon a planet and be done with it. So Metzger puts a lot of emphasis on our third criterion, that the definition must mark out natural categories. Ganymede and the Moon clearly belong in the same category with Mercury. If standard usage disagrees with this, so much for standard usage. The geophysical definition provides a very nice, clean distinction between objects, and Ganymede and the Moon are planets. It's just arbitrary to say that they're not. I think what I would say to this is that I don't agree that this is arbitrary. I think that dynamical properties a celestial body has in virtue of how it influences other bodies, are as real and natural as geophysical properties. There's a difference between an object that orbits as a satellite and an object that isn't, and we mark out that difference by saying that satellites are not planets. I think that to focus entirely on geophysical properties is to take an extremely atomistic view of things. It ignores the contributions individual objects make to the systems of which they're a part. There's nothing wrong with taking a more holistic view. There's nothing arbitrary about taking a more holistic view and also looking at relational and dynamic properties. I mean, that's what we do. Okay, the vast majority of people would not call the Moon a planet, and that's because of its sort of dynamical properties, of the way it relates to other objects. So I think that arguing against the IAU definition by ruling out dynamical properties is the wrong way to go. I think a more plausible criticism is simply to ask, is clearing the neighbourhood the kind of dynamical property we should consider relevant for defining planet? It's obvious what's important about satellites. There's a long historical and cultural tradition of holding that satellites aren't planets. But the condition that a planet must have cleared its neighbourhood is divorced from standard usage. It's probably fair to say that most people have never even heard the term clearing the neighbourhood. So, a planet must orbit the star, yep, that's in line with intuition. Planet must be rounded by its own gravity, that's fine. Nobody says that small asteroids are planets. But clearing the neighbourhood? What's that all about? And notice that this condition in some ways makes the second superfluous, because all the solar system objects that have cleared their neighbourhood are easily large enough to be rounded. I'm not sure it would be possible for something in our solar system to have enough mass to clear its neighbourhood, but not enough mass to become rounded under its own gravity. So really this third condition is the one that's doing all the work, and it's interesting that the most important part of the IAU definition is also the part that's most far removed from people's intuitions about planets. I think this might explain some of the resistance to the third definition. To the third condition, rather. An earlier proposal that by the IAU that did garner broad support was a planet is an object that has sufficient mass for its self-gravity to assume hydrostatic equilibrium, is in orbit around a star, and is neither a star nor a satellite of a planet. On this definition, Pluto is a planet, as are Ceres and Eris and many others. In my view, this definition captures the standard use of the word planet probably better than most. I think that when people talk about planets, I think it's this definition that they have in mind. I think this is probably, this is pretty much right. This gets standard usage right. I don't like this definition, though. To me, it reflects a very traditional, conservative and ultimately incorrect view of the solar system. This kind of definition would have been fine when we had planets and their satellites in the asteroid belt, and that was that. But as you've seen, there's a lot more going on. And in principle, what's the fundamental difference between an object being held as a satellite and an object being held in a stable resonance, or an object being held at the Lagrangian points? It seems to me that we now know that there are many ways for an object to be captured by a planet. Becoming a satellite is only one of these ways. Now, the requirement to clear the neighbourhood reflects this. Not only is Pluto not gravitationally dominant, but it's gravitationally dominated by Neptune. If we're going to say that satellites aren't planets, and it seems to me that we should do, I think, the Moon isn't a planet, Ganymede isn't a planet, but if we're going to say that satellites aren't planets, I think we should also say that objects like Pluto, which have been captured by planets in a different way, are also not planets. So, ultimately, I find the clearing the neighbourhood condition reasonably plausible. There's a clear line between objects that have cleared their neighbourhoods and objects that haven't, and it appropriately captures all the ways in which planets are gravitationally dominant. However, there's one big problem with it that I'm not sure how to address. We know that there are rogue planets that don't orbit stars. Now, obviously, these are not planets per the IAU definition or per the IAU plus definition. They fail the first condition, and of course, clearing the neighbourhood simply isn't applicable to them. Now, an immediate possible fix would be to drop the first condition, that a planet must orbit a star, and with the third condition say that a planet is something with sufficient mass that it would clear its neighbourhood if it did orbit a star. But as we've seen, whether or not a planet would clear its neighbourhood depends on how far from the star it is, so there's simply no fact of the matter whether or not a particular rogue planet would clear its neighbourhood. Some people have suggested that rogue planets aren't really a problem. Gabor Basri and Mike Brown, in an article on planet definitions, suggest that the definition of planet should be appropriately related to a planet's history, to its method of formation. Standardly, planets form from disks of material around stars. Planets that formed in other ways, and which would be rogue planets, aren't proper planets. So it's no problem that our definition doesn't capture them. I think this response is, it's not crazy. In general, it does often matter how things come into being. Two things that look very similar might actually be very different because they have different histories. So think of two areas of forest that look the same. One of them might be a wilderness because it grew naturally, whereas one is artificial, being planted by humans. So the idea of this response isn't bad. It's plausible that the definition of planet should relate to how planets are formed, and hence rogue planets aren't a problem. But ultimately this response still fails because there are cases where rogue planets formed from stellar disks but were subsequently ejected, and those would no longer count as planets per the IAU. Perhaps there can also be cases where planets were born rogue but were later captured by a solar system. I mean, if it turned out that Jupiter had formed on its own and was later captured by a solar system, would we say that Jupiter isn't a planet? So I think it's difficult what to say about rogue planets. Rogue planets do pose a bit of a difficulty, I think. Okay, so is Pluto a planet? Well, I don't know. I think that clearing the neighbourhood, that condition is a lot more plausible than many of its critics have suggested, but that it does have problems. I'm kind of inclined to accept the IAU plus definition, this definition, on which Pluto is not a planet. Regarding rogue planets, I think that they're a problem, but I think we can kind of just put them to one side. We really don't know much about them at the moment. We don't know much about rogue planets, and I don't think we should hold an otherwise good definition hostage to these outliers. As we learn more about them, maybe we'll have to change our definition again, but that's fine, definitions change, classifications change. This definition seems pretty good for now. On the other hand, I can also see the appeal of a very minimal definition, this one suggested by Stern, the geophysical definition on which Pluto is a planet. Okay, it also means that moons end up counting as planets, but is that such a big deal? Within the class of planets, we can still make all sorts of distinctions. Some planets are moons. Some planets are dwarf planets. Some planets are gas giants. This definition allows the term planet to be a very general term for which we can introduce more precise distinctions as the situation calls for. We can accept that there's an important difference between planets that have cleared their neighbourhood and planets that haven't, without insisting that the latter aren't really planets. I do like how simple and straightforward this definition is, and obviously it has no problems with rogue planets. It's similar to our definition of star. I mean, a star, I think, is defined in geophysical terms. A star is just anything that has sufficient mass to sustain nuclear fusion. So, maybe it makes perfect sense to give planets a purely geophysical definition. Those are the two. I mean, if we're going to define planet, I think those two definitions are probably the main contenders from my point of view. But I don't really know which one I would go for. So I guess that's it. That was a bit of an introduction to the question of whether or not Pluto is a planet. And I hope that was helpful. So that's it. Goodbye.